Dear students, in this lecture, we will study another gas field detector which is called Geiger Muller counter. It was invented by the German physicists Geiger and Muller, and that's why the name Geiger Muller counter. It consists of metal cylinder which is also called GM tube. The walls of chamber acts as cathode and a tungsten wire placed along the axis of tube acts as the anode. Thin mica window at one circular end of the cylinder allows the incident particles to let in the chamber. A glass bead is fixed at the end of the anode wire to stop corona discharge. Corona discharge is the process in which a high positive potential is applied to anode, due to which electric field at sharp end of the anode wire is so high that it ionizes the gas in the chamber. The electrons of ionized gas are collected at the anode, which is called corona discharge. Well, this has nothing to do with coronavirus. We need to stop this corona discharge, so this glass bead being insulator does this job. The gas filled in the chamber is a noble or inert gas such as helium, neon or argon. Now let us discuss the working of GM counter. As ionizing radiation passes through the gas, the molecules of the gas are ionized. Due to the high potential difference between the anode and cathode, the resulting positive ions and electrons accelerate toward the cathode and anode respectively. Electrons gain energy while traveling toward the anode and produce secondary ionizations. The electrons produced in these secondary ion pairs along with the primary electrons continue to gain energy as they move towards the anode and produce further ionizations. Now, next we will discuss the quenching effect in GM tube. When a positive argon ion reaches the cathode, it captures an electron from the cathode surface. Because the ionization potential of argon gas, which is 15.7 electron volt, is greater than the work function, which is 5 electron volt of the cathode surface. In this process, the argon ions become neutral atoms but in excited state. As a result of its de-excitation, photons are emitted. These photons, while hitting the cathode surface, eject electrons by photoelectric effect from the cathode. This photoelectron is accelerated toward the anode. It also acquires sufficient energy to initiate the ionization of gas once again, due to which another avalanche is produced. Therefore, ionization occurs repeatedly and never stops once it is initiated by the incident radiation. Consequently, a repeated discharge at anode takes place. In this situation, the detector can never be ready to detect the next incident radiation. And the mechanism used to stop this effect is called quenching. Quenching can be achieved in two ways. External quenching. In external quenching, the external circuit consisting of resistance and capacitance is used to decrease the voltage across the tube. After the ionization process caused by the incident particle, the voltage is lowered to such an extent that the photoelectron does not gain enough energy to cause another ionization. The time period for the voltage drop is given by the product of resistance and capacitance. which is of the order of few hundreds of microsecond. During this time period, the counter is recovered to the original operative voltage to detect the next radiation. Internal quenching is achieved by adding a suitable gas having lower ionization potential than the filling gas to achieve internal quenching. Internal quenching is done with the two types of gases, one halogen quenching and other organic quenching. In halogen quenching, halogens such as bromine is added to the inert gas. In organic quenching, ethyl alcohol, that is C2H5OH, is used. Quenching gas is added in small amounts, which is about 10%. These quenching gases have lower ionization potential. The ionization potential of bromine is 12.8 electron volt and that of ethyl alcohol is 11.3, which are lower as compared to argon gas, which has ionization potential of 15.7 electron volt. The inert gas ion collide with molecules of the quenching gas and transfer their charges to them. The inert gas ions are neutralized, therefore only molecular ions of the quenching gas reach the cathode. When the molecular ion of quenching gas is very close to the cathode, it captures an electron from the cathode surface to one of its excited level and becomes neutral but in excited state. The excess energy of neutralized quenching gas molecule is used to dissociate the molecule itself, hence the repetitive discharge is preventive. Next, we will discuss the graph between counts and the voltage across the GM tube. As you can see in this plot, there are no pulses at voltage below the starting voltage Vs. As voltage increases, the counting rate increases until the threshold voltage Vg is reached. Above Vg, the counting rate remains almost constant over a certain voltage range. This voltage range is called the Geiger plateau region. This is the voltage range in which the GM detectors are operated, since they are stable against any voltage fluctuations in this region. Beyond the plateau, a continuous discharge takes place and counting is not possible in this region. Operating voltage can be calculated as V1 plus 1 over 3 into V2 minus V1. Now we will discuss the dead time of GM tube. All the electrons produced during ionization of gas reach the anode wire within a fraction of microsecond because of their small mass. The positive ions proceed at the same time towards the cathode. However, being heavy particles, they proceed at a slow rate compared to the fast moving electrons. As in this figure, you can see that at the time of ionization, both electrons and positive ions are present around the anode. But after a fraction of a microsecond, after the ionization, the electrons have reached the anode wire, whereas the positive ions are still stranded around the wire. The presence of the positive ion sheath around the anode wire lowers the electric field below the Geiger threshold. A particle entering the counter at this time is thus unable to produce an ionization. As the positive ion sheath moves towards cathode wall, the electric field increases again. However, since the positive ion sheath is still unneutralized within the counter, so if the particle enters and causes ionization in the tube before the threshold voltage is recorded, a premature pulse is formed which will not be recorded by the counter. The time elapsed between the recorded pulse and the premature pulse is known as the dead time. Dead time is of the order of 50 to 100 microsecond in many of the Geiger counters. Next, we will discuss recovery time. After the dead time, the electric field is at the critical point. It allows the counter to detect ionization radiation, but the electric field is not still built at all the way back up to the magnitude that it was. Therefore, during this time, the pulses of a reduced height are formed. The time that it takes the GM counter to build the electric field back up to full strength after a full Geiger discharge is known as the recovery time. Recovery time is the time interval that must be elapsed after a pulse has occurred before another full size pulse can again occur. The full size pulses cannot occur until all the positive ions have reached the cathode surface. We can also define resolving time. Resolving time is given by dead time plus recovery time. Now we will discuss the formula of dead time. If n is the number of particles per unit time recorded by the detector and n is the actual number of particles entered per unit time in the tube, then dead time is related as capital N is equal to small n 1 minus n tau d, where tau d is the dead time of the tube. GM counter can detect various particles such as alpha particles, beta particles, and gamma radiations, but it is mainly used to detect beta particles because of its high efficiency for beta particles.